So, as I was saying, we have to add nucleotides to a 3' end. So as the helicase keeps exposing more and more parental DNA, primase has to keep coming back and making new primers that we can extend. So this is what's referred to as lagging strand synthesis, because it is slower. It takes longer for this strand to get made because we have to keep starting over. And you can see that we're making it in pieces. Here we just keep elongating an existing strand. We're making one new continuous strand. This is a double-stranded molecule. This is a sort of double-stranded molecule where most of this DNA has a complementary strand, a matching strand, but it's in pieces. And those pieces have RNA at the end. So we have two problems here. This isn't a continuous strand. It's got a nick in the backbone. And that green is RNA made by primase, which makes primers out of RNA, because RNA is what you can do strand initiation with. So, we need to deal with this. And we're going to do this. First thing we're going to do is we're going to remove the RNA. We don't want to seal the backbone until we've gotten rid of the RNA. We need our new double-stranded DNA molecule to be all DNA. So this is where we need another polymerase. So I told you the polymerase that's doing this main strand elongation is DNA polymerase 3, because it was the third one that got discovered. DNA polymerase 1 is the other DNA polymerase that's involved in DNA replication. It's much slower than DNA polymerase 3, but it has a superpower DNA polymerase 3 doesn't have. It can remove the RNA and replace it with DNA. So right here, DNA polymerase 3 is cruising along, adding nucleotides to the 3' ends. So DNA polymerase 3 is doing all of the strand elongation here. It just keeps adding nucleotides to the 3' end of this daughter strand as the helicase exposes more template. Every time primase makes a new primer, DNA polymerase 3 has to come back and grab that 3' end and start doing strand elongation. It's going to do that until it runs out of template. But when it adds the nucleotide whose base pairs to this base of the template strand, now it's out of template. The next base in the parent strand already has a partner. It's base paired to the first nucleotide, the first RNA nucleotide at the 5' end of this next primer. DNA polymerase 3 at that point says, oh, I'm out of template. I'm done. Cool. And leaves. Goes looking for a new 3' end on a new primer. DNA polymerase 1 then comes along and says, I don't think so. That's RNA base paired to DNA. That shouldn't be there. And so what DNA polymerase 1 will do is, one at a time, it will remove the nucleotide at the 5' end of the RNA primer. Now it can see that nucleotide, that base in the template strand. It can see the template. And then it will add, it's a polymerase, so it says, hey, I've got a 3' end here. I've got a template. Add the next nucleotide. So it will extend the 3' end of this daughter strand. And it's going to keep doing that until it has removed all the RNA. So it has removed all the ribonucleotides and replaced them with deoxyribonucleotides. So it's all DNA now. Once it has done that, once there's still a nick in the backbone, but now it's now it's between the 5' end of one piece of DNA and the 3' end of the next one. Last of these enzymes that you need to know is ligase. Ligase ligates, joins the ends. It can't do that when one of the ends is RNA. Ligase can't join an RNA to a DNA, but it can join two ends of DNA. So DNA polymerase I, its job is to remove the RNA primer that was made by primase and replace it with DNA. And once that has happened and all the nucleic acid in this strand is DNA, now ligase can come in and join those two pieces into one continuous molecule. Okay? So this is a kind of scary looking picture. It's got everybody. So these are the 5 enzymes that you need to know. This is another one of those things, not unlike the parts of the cell. You can see the question coming. There's only 2 ways I can ask this question on next Tuesday's exam. I'm either going to give you all the enzymes and I'm going to say, tell me what each of them does. Or I'm going to give you the functions. I'm going to say, name the enzyme whose function is to separate the 2 strands of the parental DNA so that they're available as template. Name the enzyme that makes primers. Name the enzyme that does the majority of building the new daughter DNA by doing the condensation synthesis, adding nucleotides to a growing 3' end. Name the enzyme that removes primers. Name the enzyme that makes primers. Name the enzyme that joins these individual pieces. The word that's on here that you haven't heard yet, Okazaki fragments, for those of you in the back who can't see it. Okazaki fragments refer to the individual pieces of DNA that get made during lagging strand synthesis. So lagging strand synthesis, remember, that's what you're doing here, where because you can only add on to a 3' end, and the DNA strands are anti-parallel, as helicase exposes more parental DNA, one of your 2 parental strands, the exposed template DNA is adjacent to the 5' end of a daughter strand. You can't add on to that. So primase has to come in and make another primer. Each one of these pieces primed by a primer made by primase and then extended by DNA polymerase III, extending off the 3' end of that primer, is referred to as an Okazaki fragment after the person who figured out that this is how lagging strand synthesis works. I'm not going to use that term again in this class, but it's in your book, it's in the figures. So each of these is referred to as an Okazaki fragment. So here we have, here's our helicase, unwinding our double-stranded DNA. Here's our DNA polymerase III, just continuously adding on to the 3' end of this growing daughter strand. We needed 1 primer back at the very beginning to get it started, and now it can just go. As long as helicase keeps exposing more template. On this strand, this is our leading strand or continuous synthesis. On our lagging strand here, primase has to keep coming back and making a new primer, so the DNA polymerase can grab the 3' end of that primer and extend. When it bumps into the 5' end of the previous primer, DNA polymerase III says, oh, I'm out of template. I've replicated all the DNA. Go me. And leaves. That's when DNA polymerase 1 comes along and says, no, we're not done. That's not DNA, that's RNA. I need to get rid of that. So DNA polymerase 1 doesn't do the main addition of nucleotides to build DNA. It's way slow. It's literally like 100 times slower than DNA polymerase 3. But what it can do, that DNA polymerase 3 can't, is it can take out RNA and replace it with DNA.
So DNA or polymerase 1 takes off the entire nucleotide, it doesn't just take off the oxygen.
Right, it takes off the entire ribonucleotide, throws it away, so now you have one base in the parent that doesn't have a partner, and then it can add on to the 3' end. Yeah, it is completely removing the ribonucleotides and replacing them with deoxyribonucleotides. And then once it has replaced all those ribonucleotides, so this Okazaki fragment and this Okazaki fragment are both, this one here, this is now all DNA. All that RNA has been removed and replaced. Now, when we've got DNA on both sides of that break in the backbone, ligase can seal the backbone. Okay? This is the version that's in your book. And like so many things in your book, this has more detail than you need for this class. So here's primase, making a primer. Here's helicase, unwinding the helix. Here's DNA polymerase. This is going to be DNA polymerase 3, extending off the 3' end. All the things I've crossed out, ignore them. You do not need to know anything about topoisomerases or single-strand binding proteins or sliding clamps or any of that nonsense. You'll get a bunch of that in molecular. And here's your book's version of lagging strand synthesis. Again, don't worry about any of the stuff we didn't talk about. I would recommend stick to my version here that I stole from a different book. It's got everything you need and nothing you don't. Okay? Any questions? Yes?
Ligase pushes the DNA together.
No, ligase cannot do anything if there's a missing nucleotide. The only thing ligase can seal is where you have here's my parent strand. Here's my newly made daughter strand. When I've got this nucleotide and this nucleotide, but there's a nick in the backbone, ligase can catalyze the formation of that bond there and seal that nick. If you are actually missing a nucleotide, if DNA polymerase 1 has removed that nucleotide but hasn't replaced it yet, ligase can't do a thing with that. Ligase is not a polymerase. It cannot add a nucleotide to an end. Other questions?
For that, what primates need to come back in?
This would be, so in this case, DNA polymerase would be, so most likely, this was the last nucleotide of an RNA primer. DNA polymerase used its DNA polymerase 1 used its superpower to remove that RNA nucleotide and then add a nucleotide here with the matching base. Now we've got a nick that's between DNA and DNA, not between DNA and RNA. Okay? Yeah, that's a really important difference. That's a nick in the backbone. There's no nucleotides missing. That's a gap. A gap has to be filled in by a polymerase adding another nucleotide to this 3' end. a nick, all the bases in both strands have partners, it's just one of the backbones isn't sealed. Other questions? All right, then the last